Then we separated this crude heaters and cabin heaters and VC heaters. And we looked at the firebox height and diameter ratio or firebox height to width ratio. For cabin heaters, we found that H by W was around 2.1. Most average number of burners in cabin heaters was around 20. Design heat release of each burner was about 12.1, and the floor heat flux was about 238,000. Floor heat flux is a new parameter, and it is based on the total heat release divided by the floor area of the heater. It has become important in the past 10 years because of ultra low NOx burners. Burner vendors tell us that this number needs to be around 300,000 to get good NOx reduction. So we have started publishing and calculating these numbers. For the vertical cylindrical heaters, we found that the H by D ratio, height to diameter ratio, was about 2.4. API allows up to 2.75. These crude heaters had an average of about 12 burners, each with a heat release of 13.5 million BTUs. Surprisingly, the floor heat flux, what we calculated was about 370,000, 50% higher than the cabin heaters, and I think almost on the higher limit or even exceeding the API limit, which is still not in published, around 300,000. So that's basically what our finding. So I think we were trying to calculate, assemble all this data and see how we can improve the reliability of fired heaters. We looked at the burners. The burner size, as I said already, was 12 and 13.5. We looked at the burner to tube distance. We think that is also an important parameter. And in cabin heaters, it was about 5 feet 3 inches. And in VC heaters, it was slightly more, like 5 foot 9 inches. I think it goes along with the heat release. And these are meeting API 560 minimum clearances. We also looked at the air side pressure drop, and I will talk a little bit more about that. In cabin heaters, it was generally around 0.4 inch. That is basically the draft available for the burner sizing or burner to operate. In the VC heaters, the draft available was about 0.6 inch, especially because of the height of the radiant section. So this was our survey of 30 crude heaters. If you want us to include your crude heater, you can send us the data, and we will include your crude heater in our analysis, and we will share the complete results of our crude heater survey. It will benefit you also. So what we were trying to do was to identify critical design parameters for the crude heater, and we can separate them into two sides, coil side and fire side, just like, because in any furnace, heat transfer is starting from the fire side, but ultimately it is going into the tubes. That's where the fluid is. So both sides are equally important. On the coil side, we identified fluid mass velocity, average heat transfer rate, and coil size or the pipe size. So we thought we need to focus on these parameters and optimize them to get the lowest coking rate. Average heat transfer rate is one of the most important parameters controlling the radiant section size in any crude heater. So let us talk about the fluid mass velocity. Fluid mass velocity is mass flow per unit area. The units are pounds per second plus foot square. The average mass velocity for the 30 crude heaters was around 280. The fluid mass velocity is based on the heater coil size and the number of passes. The coils are generally available in fixed sizes like pipes 4, 5, 6, and 8. The number of passes are also in the multiples. Now, as you will see, pressure drop is proportional to the mass velocity square of the mass velocity. The inside heat transfer coefficient is proportional to the mass velocity raised to the power 0.8. And film temperature is inversely proportional to the inside heat transfer coefficient. That means if your inside heat transfer coefficient is high, you will have lower film temperature. And coking rate in heaters is directly proportional to the film temperature. So if your film temperature is high, you will have more coking rate. And if your film temperature is low, you will have less coking rate. And it's basically about every 26 degree increase in film temperature doubles the coking rate. So you can see the importance of fluid mass velocity, and our recommendation is optimize the fluid mass velocity in your heater. That will be our recommendation. The second parameter we are going to be talking about is average radiant heat flux recommendations. Fired heaters are based on empirical correlations. We can design a crude heater for 8,000, 10,000, 12,000, or even 14,000 average radiant heat flux. The issue is the radiant size and heat run length. The average number for our 30 heaters was around 11,000, but here I have collected the literature recommendations. Article by Berman recommended 10 to 14,000. Nelson Petroleum Refining Engineering recommended from 10 to 15,000 BTUs for crude preheating up to 600. So we are shooting up to 700. So that's typically, but if you look at the different references, everybody is around 10 to 12,000 number. The third thing we want to talk about is the coil size. And as I said, they are available in different pipe sizes. I just want to tell you that if you use smaller tubes, we will end up with having more passes. Now, smaller tubes are better for heat transfer. They offer higher surface to volume ratio. They also offer higher inside heat transfer coefficient for the same mass velocity. Now, the downside is more number of passes require more piping and instrumentation at the inlet and outlet. So my suggestion is we should look at all the options. We should look at 4-inch, 5-inch, 6-inch, and see which one offers you the best coking rate or which one offers you the best design. Historically, most end users have preferred large tubes and lowest number of passes, but it's always good to optimize some of these things, So let us move to the fire side, and we examined a number of parameters what affect the heat transfer and coking, and here we are listing about 3 parameters for uniform heat transfer on the flue gas side. We think heat release per burner, that is one important parameter. Second is burner to tube clearance is another parameter. And the third is the burner air side pressure drop. It gives us an indication of flame length and turbulence in the firebox. So these are the 3 parameters. I mean, there are a lot of other parameters we can use, but what we are trying to do is to simplify the things and just tell you the 3 most important parameters. So let's start with the heat release per burner. We think it's a very important parameter to achieve long run length. If you have a lower heat release per burner, it ensures uniform heating in the radiant section. And this has become extremely important because of ultra low NOx burners. Ultra low NOx burners have very long and lazy flames. And our experience is anything more than 10 to 12 feet does not remain straight, actually, and they tend to lean towards the tubes which are in the colder zone. So we can help you determine the right burner size in your fire heaters and possibly improve your system. run length. The second parameter we are talking about is burner to tube clearance. Again, an important parameter, critical parameter. Our experience says burner flames should be as far away from the tubes as possible. And Lobo and Evans, when they did the paper 80 years ago, they called for non-luminous flames and all radiation taking place by triatomic gases like carbon dioxide and water vapors. The original API 560 recommendation was based on providing 2 feet gap between the flame edge and the tube body. That was a good measure for standard burners, but with ultra low NOx burners, it has proven to be inadequate. So that's basically, we think the burner to tube clearance plays an important role. The next thing we want to talk about is burner air side pressure drop. And there are two sources of energy. There is a fuel gas pressure and combustion air pressure. And fuel gas pressure more or less remains the same, but combustion air pressure changes in each burner depending on the draft availability and also whether it is forced draft or natural draft. So we think it's an important indicator for coking in the heaters. So uniform heat transfer, when Lobo and Evans wrote their paper in 1939, they assumed the firebox temperature in the radiant section is going to be all uniform and it will be a continuously stirred tank reactor. I want to tell you, you are hearing me going back to Lobo and Evans, like 80 years old. I want to tell you that even after 80 years, we are still using their correlations for designing fired heaters. And that's the reason I'm going back to Lobo and Evans back and forth, actually, because everybody, all heater vendors, even till date, whether you are using standard burners, low NOx burners, any type of heater, you're still using basically Lobo and Evans for your design. So basically that's the model what they used, but we all know that that is not true, especially now that we have the CFD modeling capability, and we found that the low NOx burners or high H by D ratios have flue gas temperature gradients. One of the most important parameter we are going to be examining today is the coking rate. And if we don't have coking rate, if we don't have coking in the tubes, we can run our heater forever. So we can even exceed 8 years. So this chart I'm showing you was developed by Nielsen. And it basically talks of two things. It talks about the relationship between the average radiant heat flux and the fluid mass velocity. And it worked on an issue, it assumed a relative coking rate of 1 for 10,000 flux and mass velocity of 300. And then it showed you the effect, if you use higher flux, the coking rate goes up. If you use higher mass velocity, the coking rate goes down. And today, with the computer age, everybody uses FRNC5 software, and they provide you tube by tube relative coking rate. Now, one of the downsides of this chart and FRNC5 is they are assuming uniform heat transfer all around the heater, and which is not true. So we thought, let us develop a heater coking index using the following parameters: average radiant heat flux, mass velocity, coil inside diameter. These are the tube side, and the three parameters we have added are burner heat release, burner to tube clearance, burner air side pressure drop, and came with this. So our objective is to get you the lowest coking rate, and we can differentiate between good, bad, and ugly heater designs. All these parameters are listed on API heater data sheet, so you don't have to do too much digging, maybe just a drawing or maybe data sheet. We are going to develop this crude heater coking index and issue it as an app very soon, in the possibly next a month or so. And you will be able to check your heater coking index. So let us talk about the case study we are going to be presenting today about crude heater with 8 years run length. And this goes back almost 30 years. In 93, I was working for a fire heater company. They got an order for crude and vacuum heaters for a Houston refinery. A giant EPC was executing the project. A renowned process licensor had developed the fire heater process design. The EPC company invited bids from different heater vendors. Our company supplied the heaters and they began operation in 1997. I left the company in 1996 and started furnace improvements. And in 1999, I was conducting heater training and I met several engineers who were involved in the startup and operation of these heaters. They talked about several operating issues with the crude heater. I told them, hey, I was involved in the design, but since the design was fixed and company wanted to secure the order, they had to give them the most competitive design. And the things ended over there. They contacted me a couple of years later and said that they are putting up a new atmospheric and vacuum unit in another refinery. I stressed the importance of process design of fire heaters. I told them process design of a heater and floor plan of a home have the same importance. So in 2002, we started working with their project team. The client told us that they are looking for 8 years run length for the new heaters. We took it as a challenge and told them we could do it if they are willing to work with us from the beginning. They agreed and we started working with their team. The client was working with an EPC company for the whole project. We gave them the process requirements. We developed a thermal design. We developed several different configurations to suit their plot plan, to suit their budget. We looked at air preheater. We looked at waste heat recovery. We even looked at the transfer line, and we were able to improve the transfer line, what EPC company was doing, and we were able to save them about 14 pounds of pressure drop. So, I mean, although the transfer line is more important in vacuum unit, but when you're designing heaters for 8 years run length, everything counts. So these heaters were built in 2005. And we found out in 2015 that heaters have completed 8 years run length. And that is why we are presenting the webinar today or paper today, because we have been successfully able to achieve it. So how to get the best fire heater for your money. All of you know the typical procedure. It's always going to the L1, but our suggestion is higher furnace improvements, and we will give you a best design for your refinery, plot space, and other things. We will give you the data sheet. We will give you the preliminary GA drawing. And this package, you can give it to the EPC. EPC can issue it to all the heater vendors, and you can pick the lowest vendor successful or the lowest price. So you will end up as a winner with the best design and lowest cost, instead of a loser when you go for the lowest cost heater upfront and then you are shutting it down and cleaning it every 2 to 3 years. So that's where the difference is. So this client wanted to put a 200,000 barrels per day crude unit in the refinery. They gave us the flow rate, they gave us the duty, they gave us the temperature, inlet temperature, outlet temperature. They told us they want horizontal tube cabin heater. I mean, that was their preference. So we designed a horizontal tube cabin heater.